right, we're going to do some modeling with exponential functions where it gives us a scenario. We have to come up with a function that matches that scenario, and then we'll use that to answer some questions. So the first situation here involves rabbits at a state park. It says the population is out of control. In 2010, we had 200 rabbits. But since then, since 2010, the population has taken off and has tripled every 5 years. And we want to come up with a function that represents this, where we could plug in any number of years after 2010, and it would tell us how many rabbits would be in the park. And one thing you can do to kind of get an idea of what's happening here is create a table. So in our table, we've got T is the number of years, and then R of T is the number of rabbits after that many years. And we know this starts in 2010. I'm going to write that off to the side. For purposes of our function, we want to think of 2010 as year 0. That's when it all starts. So after 0 years, when this starts, we know we have 200 rabbits. Now it tells us it's tripling every 5 years. So the next year we want to look at is 2015. That's 5 years in, and we know the population is tripled. So if we take the original 200 and triple it, we're going to end up with 600. Okay, 5 more years would put us at 2020. That would be 10 years into this situation. It's going to triple again. So 600 gets multiplied by 3, and we have 1,800. And we could continue doing this and keep multiplying by 3 and adding 5 and get an idea of how many rabbits we'd have at each of these 5-year periods. But that could take a long time. So let's see if we can set up a function that's going to do a lot of this work for us. So it tells us we have R of T, and we know we're going to start with 200 rabbits. And we know we're going to multiply this by something. We have to figure out what we're multiplying by and how that's going to be represented. So here's one way to think of it. At year 0, so we have R of 0, rabbits after year 0, it's just 200. After 5 years, year 5, so R of 5, we have 200, and we multiplied it by 1, 3. Okay, after 10 years, we had 200, multiplied it by 3, and then multiplied it by another 3. So we multiplied by 2 3s. After 15 years, we'd multiplied by 3 3s. We started with the original and multiplied by 3 times. So what you can see here is after 5 years, we multiply by 1 3. After 10 years, we multiply by 2 3s, or 3 squared. After 15 years, we multiply by 3 3s, or 3 to the third. So if you look at the exponents we're getting on the 3, the exponents are whatever number of years we have divided by 5. So after 5 years, we're multiplying by 3 to the 1. 5 divided by 5 is 1. After 10 years, we're multiplying by 3 to the second. 10 divided by 5 is 2. After 15 years, we multiply by 3 to the third. 15 divided by 5 is 3. So the idea here is we're taking 200, we're multiplying it by 3 a certain number of times, and the number of 3's we multiply by is the number of years, T, divided by 5. So if we wanted to know the number of rabbits in this state park after 25 years, we would plug 25 in for T, take 25 divided by 5, which would be 5, and we'd have 200 times 3 to the 5th. So that's how we set that equation up. And I'm going to write that equation over here under the rabbits so we have it to refer back to. So R of T is equal to the original 200 rabbits times 3 rabbits for every T over 5 years. All right, or every T years divided by 5 is how I should have said that. Sorry. Okay, now we're going to use that function to answer these next couple questions. It says, if this growth continues, how many rabbits will we have in the park in 2050? So we have to remember our situation starts in 2010. 2010 is year 0, so 2050 is 40 years into this situation. So what we're going to do is we're going to take our function and we're going to plug in 40. So we're going to say R of 40 is equal to 200 times 3 to the t over 5 power, but again, t in this situation is 40. So 3 to the 40 over 5 power. Now we can simplify this just a little bit. 40 divided by 5 is 8. So we'll have 2 times 3 to the 8th power. And at this point, you just got to go to the calculator. So I will do that. And we have 200 times 3 to the 8th power. And that's 1,312,200. So that's how many rabbits we'd have after 40 years, is 1,312,200 rabbits. So that's our answer for the second part. Third one says, at this rate, how long would it take for the rabbit population to reach 10,000? Well, one thing we know right away is after 40 years, it's going to be over 1 million. So 10,000, it's not going to be, it's going to hit that well before the 40-year mark. But this might be a good thing to know because chances are the rabbit population is not going to grow like this forever. And maybe they know that once they hit 10,000, that's when they really have a problem. So they need to know how much time do we have before it hits 10,000. So we can figure that out using our function here. So, grab another color. I'm going to work this out off to the side. We have this r of t equals 200 times 3 to the t over 5 power. And this one, we know the final answer. We know the final result is going to be 10,000. So that's going to be r of t. That's what we would get after working this out if we actually knew the value of t. And then we have 200 times 3 to the t over 5 power. So we're trying to solve for t, which is stuck in an exponent right now. And the first thing we need to do is divide by the 200. I'm going to take care of that first. So take care of that initial amount first. Divide that out. And when we divide that, we're going to end up with 50. And then 50 equals 3 to the t over 5 power. Now, the problem we have is our variable is stuck in the exponent. And the only way we can get a variable out of an exponent is to use a logarithm. And so what we're going to do is we're going to take a logarithm of both sides. So we're going to say log of 50 equals log of 3 to the t over 5 power. And the reason we do that is because when you have an exponent in a logarithm, what you can do is you can pull it out front. So you may remember doing this. So we can rewrite this as log of 50, and I'm really squeezing it in here, equals t over 5. So I pull that exponent out front. It becomes a coefficient times log of 3. So now the t is no longer in the exponent, and I can use it. I can solve for it now. So what I need to do is get the t by itself. I'm going to divide by log of 3. Those are going to cancel out. And I'm going to need to write this elsewhere where I have a little more space. So I'm going to move over right here underneath the word rabbits. So we have log of 50 divided by log of 3 equals t over 5. Now, the only thing I need to get rid of now is that 5. So I'm going to multiply both sides by 5. And what I'm going to end up with, to figure out what t is, I've got 5 times log of 50 divided by log of 3. So once again, go into the calculator. So we have 5 times log of 50. I'm going to go ahead and hit equals. I'm going to divide by log of 3. Hit equals. And I get 17.8, approximately 17.8 years. So we're going to say 17.8 years rounded to the nearest tenth. So that's how long it would take for the number of rabbits to get to 10,000, 17.8 years. All right, now we've got wolves. Situation's a little bit different. So let's look at what they're telling us here. It says wolves were reintroduced to a national park 10 years ago. So we are going back in time 10 years. Since that time, the wolf population has doubled every 4 years. So doubled every 4 years. There are currently 198 wolves in the park. Now, if we want to create a function here, we would say, we can say W of t is equal to the initial amount. And we don't know the initial amount. Like when we had the rabbits, we knew we started with 200 rabbits. Here we don't know how many wolves we started with. So I'm just going to call that x times the amount we're increasing by. So here it's doubling, so we're going to multiply by 2. And then we would say, since it's doubling every 4 years, what we would do is we would do t over 4, just like we did t over 5 on the previous problem. So here's the issue we have, though. We don't know that initial amount. And we need to find that because that's actually the first question it's asking us, is to find the initial size, the initial amount of the wolf population 10 years ago. So to do that, here's what we can use. We know a period of time. We know a number that we can plug in for t. And we also know the number of wolves that we will have after that 10 years. We know we end up with 198 wolves. So we can plug in both of those numbers. So we can say W of t, after 10 years, we've got 198 wolves. We still don't know what we started with, but we know 10 years have passed. So we can plug 10 in for t. We have 10 divided by 4. So 198, the amount of wolves after 10 years is equal to the number of wolves we started with times 2 to the 10 over 4 power. And I'm going to simplify that a little bit and write that as 2 to the 5 halves power. I'm going to simplify my fraction. So I don't know that you necessarily need to do this part. You could make that exponent into like a decimal if you wanted to, and then just plug it into a calculator. I like to think about what that actually represents. So 2 to the, and I'm just going to do this off to the side, 2 to the 5 over 2 power is going to be the square root, the second root of 2 to the 5th power. 2 to the 5th power, 5 looks like a 6, let me fix that. 2 to the 5th power is 32, so this is equal to the square root of 32. So what we got here is a 198 equals x times the square root of 32. So what we need to do is divide by the square root of 32. And that should tell us x. That should tell us how many wolves we started with. So I'm going to head back over to the calculator. So we've got 198 divided by square root of 32. And that is equal to almost exactly 35. So we've got 35 wolves. Now, say, let's write this down really quick. We have 35 wolves. Say you didn't want to use the radical 32, and you just wanted to keep it as 2 to the 5 halves power. What you could do is you could figure out, okay, 5 halves, 5 over 2, as a decimal would be 2.5. So instead of dividing by square root of 32, you could have divided by 2 to the 2.5 power. So let's just verify that that works. So we got 198 divided by, I'm going to put parentheses here, 2 to the 2.5 power. And when we do that, again, we get almost exactly 35. So that checks out. So 2 ways you could look at that exponent. All right. So next question. Now we've got an idea of the initial amount. We know we're starting with 35 wolves. It's asking us to estimate the wolf population 10 years from now. So the idea is the initial amount was 10 years ago. We want to go like 10 years into the past. We want to go 10 years into the future. So if you think about the total amount of time, we're looking at a 20-year time span. So we've got now, we know the initial wolves was 10 years ago. So that was the 35 wolves. And then we want to figure out how many wolves will be 10 years in the future. So that's 20 years. So what we can do is we can use our function. We can say W of t, wolves after t years, is equal to the original amount, which we know is 35, times 2, because we're doubling, to the t over 4 power. And now, since we're doing this 10 years in the future, so that's 20 years since we started, we can plug in 20. So we've got W of 20 equals 35 times 2 to the 20 over 4 power. I'm going to simplify our exponent. 20 over 4 is 5. So W of 20 is going to be equal to 35 times 2 to the 5th power. 2 to the 5th power is 32. So this is going to be 35 times 32. So we can just plug that into a calculator, and that will give us the answer. So 35 times 32. And our answer is 1,120. So after 10 more years, it'll be 1,120 wolves in that national park. Okay, so that's a couple examples. One where you know the original amount, you know the rate at which it's increasing, and you use that to set up a function and answer some questions. And then one where you don't know the initial amount, but you know some other information, and you first find the initial amount so that you can then set up a function and answer other questions. Okay, one more scenario, this time with badgers, and this time it's going to work a little differently. It tells us the badger population in a certain region has a relative growth rate. That's going to be really important. Relative growth rate of 4% per year. It also tells us that we're starting in year 2000, so that's like year 0. And at the initial population, the population back in 2000 was 2,400. So starting with 2,400 badgers in the year 2000. And it's growing at a relative growth rate of 4% per year. So relative growth rate is a sign that we are going to use our friend E. If you remember, E is an irrational number. It is approximately 2.718. And it's a number that we get whenever something is growing exponentially continuously. And so that's what we're going to use to build our function here. So when you see relative growth rate, you're going to use E. And the equation, the formula we're going to be using here, and I'm going to write this underneath the badger, it's usually written like this, N sub 0. And so that means your starting amount, your initial amount. Then times E. And then your exponent is RT. So R is your rate. And you always write that as a decimal, not as a percent. And T is, as always, the time. So that's our formula that we're going to be using. So the first thing we got to do is write a function. So we are going to call our function B of T. So badgers after T years. And we are going to start, our starting amount is 2,400 times E. And our exponent is going to be our rate. So 4%, you move the decimal 2 places to the left, it becomes 0.04. So it's going to be 0.04. And then our number of years is going to be T. That's our variable. So B of T is equal to 2,400 badgers times E to the 0.04 T power. Next thing we got to do is estimate the badger population in 2050. So now what we got to do is take this function we've just come up with and plug in this year. So here's what we have to think about, kind of like we've done on these other problems, is how many years have passed since the initial year, since 2000. So if we're at 2050, that means we've gone 50 years from our starting point. So 50 is what we're going to plug into the function. So we're going to say B of 50 badgers after 50 years of this is equal to 2,400. E to the 0.04 times 50 power. You can punch that into a calculator as is. I'm going to go ahead and multiply 0.04 times 50 because that works out pretty nicely. It's 2. 4% of 50 is 2. So it's going to be e squared, e to the second power. So I'm going to go to the calculator and type in 2,400 e squared. And I will get this right here. I'm going to round to the nearest badger. So it's going to be 17,734. 17,734 badgers, approximately. All right. Third thing we got to do, after how many years will the badger population double? Round to the nearest 10th. Okay, so what we have to think is if we start with 2,400 badgers, doubling would mean having twice as many badgers. So doubling would mean we would go from 2,400 up to 4,800. So the idea, sorry about that. The idea is we've got to use 4,800 as our B of t, as our final answer, and then figure out what amount of time, what number for t would cause us to get that. So what we're going to do is set it up like this. We're going to say 4,800, our final amount, is equal to the original amount times e to the 0.04 t. Because what we don't know is the number of years, the amount of time. So first thing I want to do, as always, is I want to divide by that initial number. So divide by this 2,400 to simplify this. And the nice thing is we know that 4,800 is twice as big as 2,400. So we know when we divide that, we're going to get 2. I'm going to erase some stuff here to give us a little extra space. All right, so now I'm going to write this down. So we're going to have 2 after we divide equals, and all we're going to have on the right side is e to the 0.04t. So like the last situation, like the rabbit situation, we have a variable that's stuck in an exponent, and we want to figure out what it is. And the only way to do that is with logarithms. But here, instead of just doing log of both sides, because we have an e, we're going to use the natural log. And you'll see why in a second. So what I'm going to do, because, I mean, it's an equation, so really you could do anything you want as long as you do it to both sides. But we're going to do natural log. And so I'm going to have natural log of 2 equals natural log of e to the 0.04t power. And as before, that logarithm allows me to take my exponent and move it out front and make it a coefficient. So you're going to have natural log of 2 equals 0.04t times natural log of e. So think for a second about what natural log is. So natural log, ln, is the same as log base e. So basically what we have here, when we have ln of e, that's log base e of e. And so what you're asking is e to what power is equal to e? Well, e to the first power equals e. So log, whenever you have a log where the base and the number you're taking the logarithm of are the same, it's always going to be 1 because you're looking at the exponent that gets you from the base to the number. So natural log of e is just 1. So it cancels itself out. You're just multiplying by 1. So it just eliminates itself. And that's why we use natural log. It's going to make this work out a lot more nicely. So now all we have to do to get t by itself is divide by this coefficient 0.04. So you have the natural log of 2 divided by 0.04, and that should tell us t. That should tell us how long it's going to take the badger population to reach this amount. So one more time to the calculator. So we have this ln button, ln of 2 We're going to divide that by 0.04, and that gives us 17.328, etc. It said round to the nearest tenth, so it's going to be about 17.3 years. So T is about 17.3 years. That's how long it would take the badger population to double. So they're not growing as quickly as the rabbits are. So there you go. That's some exponential modeling.